The last tool we're going to talk about is something called commutators. So this is again a property of operators, not the functions that they operate on. You actually know about commutators already because from your study of algebra, you know that addition, subtraction, and multiplication and division are all commutative. That is, it doesn't matter what order that you do the operation in. So in other words, if I take A times B, it's the same as B times A. That means that the multiplication of A and B is commutative. With operators, it's a little bit tricky though, because here we're talking about doing an operation on a function. And we represent a commutator like this, where we have operators alpha and beta. And let's say that they are operating on a function f. If A and B commute, then if alpha and beta commute, then alpha operating on the result of beta operating on f will be equal to beta operating on the result of alpha operating on f. And it turns out that not all operators will commute. So this is not true for all operators. So let's look at some pairs of operators and try to decide whether they commute or not. For our first example, let's make alpha equal just multiply by x and beta equal take the derivative with respect to x. So if alpha and beta commute, then when I operate on any function, that commutator will equal 0. In other words, alpha operating on the result of beta operating on f minus beta operating on the result of alpha operating on f will equal 0. So let's do this one first. So the first thing I do is I take the derivative of f. So take the derivative of f, and then alpha says multiply that by x. So I just multiply by x. Over here, I'm going to first multiply by x. So I'm going to take the derivative of what I get when I take x times f. And remember that f is a function of x. So we'll just write that explicitly. All right, so notice that now I have a product of two things that both involve x. And so I need to use the product rule. So I have x df dx from my first term here. And then I have minus the first times the derivative of the second, minus, because of this minus sign, the derivative of the first, which is 1, times the second. And so you can see that this equals f at x, because this and this cancel out, and it equals minus f at x, which is not, in general, 0. So the only time that this would be true is if we didn't have a function, the function equaled 0. And so we can say that alpha and beta, where alpha is just multiply by x and beta is take the derivative, do not commute. This is significant because it turns out that multiplying by x, this operator, is the operator that tells us about the position of a particle, where it is in space. And the operator where I take minus the imaginary number I times h bar and take the derivative with respect to x is the operator that tells us about the momentum of the particle. Now, if two operators do not commute, that means that I cannot simultaneously know with exact precision both of those properties for the particle. So because x and p, position and momentum, don't commute, that tells me that, in fact, I cannot know x and p simultaneously with complete precision. I can't measure them both at the same time. And you'll recall from the very first day of this class that we talked about this uncertainty principle and the fact that, in fact, we had to have some minimum product in that uncertainty, and that the better we knew x, the less we knew about p, and the better we knew p, the less we knew about x. And that is because these two operators don't commute. So that shows up in our model as two operators that don't commute. So whenever we have operators that do not commute, that implies that there is an uncertainty principle between those operators. So this idea of an uncertainty principle, in terms of our ability to measure things, is more general than just position and momentum. Any two operators that don't commute will have an uncertainty principle. So if the operator for momentum is minus I h bar, take the derivative, and the operator for kinetic energy, so we're going to use a T to represent kinetic energy. The operator for kinetic energy is h bar squared over 2m, take the second derivative. Let's see if we can know the momentum and the kinetic energy of a particle simultaneously with as much precision as we want. So if these two operators commute, that means that I can simultaneously know both the kinetic energy and the momentum of my particle, and I don't have to worry about any kind of uncertainty principle. Okay, so how do I do this? Well, what I'm looking for is, do P and T when I operate on any well-behaved function, does that commutator equal 0? So I need T, so h bar over 2m, take the second derivative of f with respect to x, and then I need to operate the result of that with minus I h bar, take the derivative. So now I need to subtract the result of doing the operations in the opposite order. So minus, take the derivative of f with respect to x and multiply by minus I h bar, and then take the second derivative of that and multiply by h bar squared over 2m. And I want to know, does that equal 0? If it equals 0, these two operators commute. So if I look at all of these constants, I can just lump them all together, and I have minus I h bar cubed over 2m. And then if I take the derivative of the second derivative, I have the third derivative of f with respect to x. And then over here, same group of constants, lump them all together. And then I can take the second derivative of the first derivative, which again gives me the third derivative of f with respect to x. And I can see that, minus and a minus makes this, minus and a minus makes this plus. So I can see that these are equal and opposite. And so that equals 0. And that means that my momentum and my kinetic energy commute. And that suggests that I can simultaneously measure the momentum and the kinetic energy of my particle, and I don't have to worry about any restrictions on the precision of those measurements.